Okay. All right, I want to start by reminding you where we are. We're talking about material functions in shear flow. And I previously talked about steady shear flow, stress growth of steady shear flow, and steady shear flow followed by cessation, the stress relaxation experiment. And the main parameter of shear flow is the function sigma dot as a function of time. So when that's a constant, for instance, gamma dot naught, the stress will be a constant. And the strain, which we introduced last time, is a linearly increasing function of time. So what that means is we have a sample between two plates. We're moving the upper plate at a constant rate. And it's constantly being strained. And the strain always increases. So if you imagine a little sample inside, that sample of material is being strained and elongated and rotated because of the shear flow. Okay, that's what's represented by this function gamma of 0 to t. And we defined that function, strain 2, 1, is the integral between 2 points, so let's say from 0 to t, of the strain rate function. And since we're integrating it, we use a dummy variable of integration because we don't want to get confused with the time that's in the limit. So t prime is our dummy variable of integration. And so for steady shear flow, this gamma dot 2, 1 is just the constant shear rate. And so we get the integral from 0 to t of a constant, which means we get the constant times the variable we're integrating over. We evaluate it by the limits, and we get gamma dot naught t, which is what we sketched here. So for all time, the strain is gamma dot, the strain between time 0 and time t is just gamma dot t. For the stress growth experiment, same deal. We have to specify the shear rate function, sigma dot. In this case, it's a step-up step function. For Newtonian fluids, we showed that the stress response is a step-up stress function. And for non-Newtonian fluids, the stress increases to some usually steady value, but it doesn't have to be a monotonic increase. It can show one overshoot. It can show overshoots and undershoots. It can do all kinds of crazy things. These are two typical polymeric responses: rising slowly and reaching a steady state, or overshooting once and then reaching a steady state. The strain between time 0 and t is the same calculation I just did. There's no strain below time t equals 0, but between 0 and any time t, the strain is given by the strain rate times the time, and that gives this linear function. The stress relaxation material function is based on sigma dot. That's a step down step function. So it's a constant that steps down at time t equals 0. The Newtonian response is not shown here, but it would be an instantaneous step down. And the non-Newtonian response is for it to decay with some decay time here, either a rapid decay or a slow. There's not actually as much variety in the stress response of relaxation as there is in the startup. And that's because, frankly, in the startup experiment, whatever the sample has been resting for a long period of time, and it usually picks up some kind of structure by settling into some preferred structure. And so this overshoot is actually the breaking of that structure. In the case of liquid crystal materials, they're the ones that show overshoots and undershoots. Those materials have structure inherent in their liquid state, their liquid crystal state, and you're constantly breaking and reforming structure in that case. The strain between time 0 and t is once again this, it's something when the time is below 0, and then it's nothing because the shear rate goes to nothing greater than 0. Now we've been talking about the 3 more material functions: creep, step strain and small amplitude oscillatory shear, and we've thus far talked about creep. And creep was complicated and got us into the idea of strain in the first place. In the creep experiment, which I'll show those slides again, somehow one of the curves disappeared, but there's a step up in the stress here, which is different. We're no longer specifying sigma dot of t. It's the only one. I really don't know what happened to my slides. A bunch of lines have disappeared. There they are. They're back. Okay, a little Microsoft addition. So there's my step up. In the case of both step strain and small amplitude that we'll talk about today, you still specify the shear rate function. Creep is the only one where you specify the stress instead. And here you step up in stress, and the Newtonian fluid steps up in rate, and the strain is aligned just as it is in step up in rate experiment, the startup experiment. But for non-Newtonian fluids, it does not step up in rate. The rate also takes some amount of time to adjust, and it can overshoot. And in strain, when you actually monitor how the material responds to the stress, it's various nonlinear functions. And this was what we saw in the movie, as I pointed out last time. This was a displacement, which is related to strain. And you see that it jumped up and then became a straight line. It didn't immediately go to becoming a straight line, and that's a non-Newtonian response. So we ended the class last time by doing a calculation of what the compliance was, which is based on this strain function. So this was my example of stress, constant stress-driven flow. The stress was applied by using a pulley and a mass, which therefore in a gravity field F equals ma. While the acceleration due to gravity is a constant, so the force is constant. The cross-section that's touching the fluid is constant, so the stress is constant. And we did this discussion of strain. So strain is a complicated topic. We're going to talk about it now. We've gotten to the one equation we need, which is that the strain is the integral of the strain rate. We're going to drop it for a while, and then when we talk about advanced material functions, advanced constitutive equations, we're going to be back to talking about strain again. Because it's going to turn out that in order to fix the things that we're going to find out are wrong about the constitutive equations we have, we're going to have to consider strain. We're going to have to think about these materials as more solid-like instead of as more liquid-like. Because it's our inability to take into account the fluid memory that comes with a solid elastic material that's messing up our equations. So we'll be back to strain. So if you don't get it now, ask your questions and we'll get them sorted out. And then this will all be very clear when we get to chapter 9. So we went over a little bit of strain. Strain involves following material particles around. It's much more complicated than strain rate in simple homogeneous shear flow. So we have the location of this point at 2 times. We can write the location of that point at those 2 times mathematically by its location vector. The displacement function is the distance between. It's the vector that connects these two. It's a vector. We can define strain as a tensor that's related to this vector. We won't do that just now. Keep things simple. Only talk about shear strain. Strain is really a tensor, however. When you think about strain, about deforming a complex fluid by squeezing and rotating it, it's certainly happening in 3 dimensions. And you have to ask, it's very complicated to describe a change of shape that you might take by taking a piece of silly buddy and squeezing it in your hand. It requires a tensor. So we're going to approach that gingerly, because it's actually an even more complicated tensor than stress. So in our case, for shear, there's only one strain that's important, so we leave life simple and only talk about the shear strain. This will generalize to the full tensor version, but for now we'll just use the shear strain. So all we need is this displacement function. Once we have it, we can then take this derivative and get the shear strain, and that's what we did. So we wrote the displacement function by looking at the geometry. The position at time t ref is just a given. The position at some later time is the initial time, the initial location, plus the change in location, because this is shear flow and it's a very simple flow. And it only moves in the one direction, so there's only a change in the one direction. The 2 component of the location and the 3 component do not change. Once we've written these 2 R's, we can subtract them. That's easy. We just subtract term by term. We get the displacement function, and we can take this derivative. There's U1. Its derivative with respect to x2 is just the stuff in front, and so that's the strain. So we calculated that the strain was the time times the shear rate, and I also went through a discussion about steady and unsteady shear flows, which I think in summarizing will probably just make it more confusing. So I'll just point out the conclusions. In steady shear, the strain is T gamma dot. In unsteady shear, the strain is the integral of gamma dot with respect to time. That's the bottom line. It kind of makes sense when you look at this final equation, because this is a rate. So when we integrate strain rate, we should get strain. So that makes some amount of sense. The other thing to notice about strain is it's always between 2 specified points. You can't just say, what's the strain now? No, you have to say, what's the strain between this location, this shape, and that shape? Okay, what's the strain between this shape and that shape? This shape and that shape? Or from the initial shape to the final shape. You always have to say for strain between some starting shape and some stopping shape. Or in the case of this flow, some starting time and some stopping time. So then we got specific. We went back to the creep and defined it. So in this case, it's a step-up function in stress, and we have to deduce the motion of the material. For when we know the constitutive equation, we can do that. When we have the material and we have an instrument that does this, we can measure it. Okay, so those are the 2 ways that material functions are used. And the only constitutive equation we have is the Newtonian one, so we did the derivation of the creep material functions for the Newtonian. The creep material functions were not based on this rate function, but rather its integral, the strain function. And that's related to that measurement that was done like in the video. So this was the derivation I ended class with, so let me put that back up. We said we're considering shear creep. What is the shear creep compliance for a Newtonian fluid? The definition of compliance is back over here. We need the strain as a function of time. Strain is the integral of rate, which means we need rate. So if we had the rate, we could integrate it and get the strain, so that's fine. But what we have is the stress. We put the stress on the sample. We put this into the constitutive equation. We then calculate the strain rate. Then we integrate it to get the strain, divide it by minus tau, and we get the compliance. So how did we do that? We started with the constitutive equation, and we were trying to put this into it. Okay, how do we put that into it? Well, our goal is to calculate the strain rate. Strain rate's going to have velocity derivatives in it. You know, this is the gamma dot tensor. And we want the 2-1 component of that tensor. That's what appears over here that we want to integrate to get this, that we want to divide to get this. So it's all step-by-step calculation. So we start by generating this tensor. So we have the velocity field, except we know it's a shear flow, but we don't know what that coefficient is. So we just put an f in there, f of t, to hold that spot, and we'll solve for that. So this is shear flow in general. There's the unknown function. We can then take this v and go del v plus del v transpose. So we did that. Del v plus del v transpose. So del v we wrote out in Einstein notation and then wrote up in the tensor notation. the matrix notation. 1, 2, 3, coordinate system. And then we just simplified it because the velocity is f of t x2, 0, 0. v2 is 0. v3 is 0. v1 is not a function of x1. v1 is not a function of x3. And v1 is a function of x2, and the derivative, partial derivative of v1 with respect to x2 is just f. So we put that f in there. So we get 0, 0, 0, f 0, 0, 0, 0, 0. We add f and its transpose, and we get the gamma dot tensor. And we look at it and say, what is the 2, 1 component? And it's just f. So this we can plug into the constitutive equation. This is the constitutive equation for a Newtonian fluid. Tau equals minus mu gamma dot. So there's gamma dot multiplied by minus mu. I get the stress tensor. And the 2, 1 component of that stress tensor is minus mu f. So the 2, 1 component is what was specified in the shear creep compliance material function. It's 0. This is what f must be. It must be whatever it needs to be to make this 2, 1 component be what we impose. So this 2, 1 component is got to be 0 for time t less than 0 or tau naught for t greater than 0. That has to be equal to minus mu f. So when we divide by minus mu, we get 0 for time less than 0, and we get tau naught over minus mu for time greater than 0. And this f of t is just equal to gamma dot 2, 1. So that's the function we needed in order to make our calculation. So I'll redo that. Now we've got gamma dot 2, 1 of t is equal to 0 for t less than 0 and minus tau naught over mu for t greater than or equal to 0. And the strain, which is the one we need in order to get compliance, is the integral from 0 to t of gamma dot 2, 1 of the dummy variable dt prime. So we can carry out that integral. Well, how do we do it? Well, we only want the integral between 0 to t. We know the function for all time. But between 0 and t, it's clearly equal to just this second part. We don't need the first part, because this includes the entire domain over which we're integrating it. So the integral from 0 to t of gamma dot 2, 1, that's this function, which is minus tau naught over mu between those limits, dt prime. We're integrating with respect to t prime, so when we integrate a constant, we get the variable, and then we evaluate the variable between its limits, and we get minus tau naught over mu t minus 0, or minus tau naught over mu times t. So this says that a Newtonian fluid will have a strain that's equal to this quantity. It's linear with time. Now we go back to our definition of the material function. We've got the quantity we needed. Now we just plug into this definition to get the compliance. So J of time is defined as gamma 2, 1 between 0 and t divided by minus tau naught. We've got it. So it's minus tau naught over mu times t over minus tau naught, or t over mu. if we sketch it, J of t for a Newtonian fluid is a straight line with a slope 1 over the viscosity. If this is the response we measure, and then we measure it again for a material that's twice as viscous, what does it look like? Twice as steep?
Wait, no.
Half as steep, right? If I double the viscosity, this denominator gets bigger, which means the ratio gets smaller. So this is 1 over 2 mu. So does that make sense that if I have a material between two plates and I put a constant stress on it, let's say it goes this fast. If it's more viscous, does it go faster or slower? Slower. So for the same amount of time, it goes half as far, right? Is that what this says? For the same amount of time, it goes half as far. Compliance is backwards. Compliance is how much does the sample allow motion? When it's viscous, it does not allow much motion. When it's inviscid, when it's really thin, that stuff goes nuts. It's steeper. So if the viscosity is 1/3 the viscosity, let's say, that would be 3 over mu, and it would go a lot faster. And this is what he showed in the video also. He didn't show it as a function of rate, but he showed these lines. I'll show you what that looks like. This was his Newtonian case. He put a constant stress and caused it to move, and it's a dead flat straight line, okay? Straight slope here. That's the Newtonian response. Now, I have a bunch more slides on creep, but I really don't want to go into all of them, so I'm going to skip a bunch. Here's the function that we just derived. The compliance is, it's not moving, then it moves. If you stop the flow at some time, this is exactly what it did in the experiment. It just leveled off. Trying to change color. There we go. So it doesn't move, it moves, and then when you stop the flow, it levels off. For a non-Newtonian fluid, as we saw in the video, it takes some amount of time to get to a steady state. At this point where the slope is constant, that's the steady state. And it turns out, which you'll just have to take my word for it for the moment, that this slope here is 1 over the steady shear viscosity at the ultimate shear rate of this sample. So this is actually a very chock full of energy kind of a material function. There's all kinds of aspects of this curve that are measured. And again, I don't want to go into it. There are details in the text if you're curious about this type of an experiment. If you stop the flow, which was done in the movie, and allow it to recoil, you can also measure parameters that are related to recoil. And if you go back to my creep material functions, I did define a recoverable creep compliance that's related to how much does it spring back after the flow is over. So that's related to this amount here. How much does it spring back? The details are in the book. This is some experimental data on creep compliance. In this material, it doesn't reach the steady state and stay at, it actually has a much more complicated creep compliance. So I'm skipping these slides. This is where I show that ultimate slope, but I don't want to take the time. And this is where I talk about the recoverable creep. Skipping. Okay, now I want to go on to the last two material function families, step strain and small amplitude oscillatory shear. So now we're back to measuring sigma dot, or imposing sigma dot. But the sigma dot that I impose is a bit complicated here, right? This is called the step strain function. Let's see if we can understand why it's called that. So we're going to do a step shear. And with all these material functions, whatever I say sigma dot is, that's what it is. And in this case, I say, it's by definition, it's the limit as epsilon goes to 0 of this function. This function is 0 for time t less than 0. It's a shear rate, a specified shear rate. This should be gamma dot naught. I don't know if that's my typo or the computer's. T between 0 and epsilon. And then it goes back to being 0. So if we sketch that, this is sigma dot of t. It's 0 for t less than 0. It's something up to t equals epsilon. This level is gamma dot naught. And then above that time, it's 0 again. So this one is, if we have the sample between our plates, we rapidly shear it for just some short amount of time. Okay, we're letting the limit of that time that we're shearing be very, very small. So it's like I instantaneously, if possible, move this to a set position. And so as we said before, as we're moving in shear flow, the strain is linearly increasing always with time. So if I very rapidly move to just one new position, I've put a step strain on the sample. Okay, I've stepped up in strain. This is strain rate. If we look at strain, it would look like this. The integral between this time and this time of a function that's 0 is 0. Okay. The integral between a time that's 0 and this time is 0 at time 0. When I'm in this region where we are shearing, the strain is going to be linearly increasing with time because we're shearing at a constant rate. The slope is going to be the gamma dot. And then once I stop shearing, again, there's no more additional strain. So this is at time t equals epsilon. This is the strain. And this final amount is the final amount of strain that's put on the sample. So this line is t times the shear rate. And at this final point, the time is epsilon. So from here on, so here the strain is 0. Here the strain is epsilon over 2 times t. Here the strain is epsilon times t. And then the strain never changes. So this is epsilon times t is the strain that it stays at. Oh, I see. I take it back. That wasn't a typo on my slide. This is a variable shear rate. This is the variable shear rate, gamma dot. And then down here, I define gamma dot naught as gamma dot epsilon times. Is that right? That's okay. Actually, I prefer my answer before. This should have a little subscript 0 on it. Okay, so this is the strain at the end, which I call gamma 0. The ultimate strain, the strain of the step. This parameter, gamma dot naught, is related gamma dot naught, the strain rate, times epsilon is equal to the strain. This, yeah, I forgot a gamma dot naught here. I'm looking for a little error here. This, this strain is gamma, this is correct. This is the function, gamma dot naught t. And so up here, it's gamma dot naught, I wrote a misstep here. I just wanted to plug in an epsilon for time, and I should have written epsilon times gamma dot naught. There's my mistake. I knew something was backwards. Sorry about that. So all I'm doing is that I'm plugging in the time for this location, which is when I know where that strain is. This is for all times, this line is t times gamma dot naught, and at this time here, t equals epsilon, it's equal to epsilon gamma dot naught. That's the strain in this step stream. Now, the material functions for this flow are defined as, just like they are in the steady shear and the startup of steady shear experiments, you measure a shear stress, a first normal stress difference, and a second normal stress difference. The material functions that are defined in this flow are moduli. This is the relaxation modulus. You take the stress and divide it by the strain magnitude. So instead of stress divided by shear rate, you divide by strain. And the first normal stress relaxation modulus is the first normal stress difference divided by the strain squared. And the second is the second normal stress difference divided by the strain squared. So we sketched the shear rate function and the strain function. We can also calculate the strain function mathematically. Okay, let's be more formal. We know the definition of strain. Let's be formal. Strain between two times is the integral between those two times of the strain rate function, gamma dot, t prime, dt prime. This strain rate function for this flow is our sigma dot. How do I know that? Well, that goes back to what gamma dot naught is, what gamma dot 21 is. That's the 21 component of this tensor. This tensor is del V plus del V transpose. V for this flow is sigma dot x2, 0, 0. So when we take this and calculate gamma dot, the tensor, we get 0, sigma dot, 0, sigma dot, 0, 0, 0, 0, 0. Because only the 2-1 component exists, and then when we take del V plus del V transpose, it shows up in those two positions. So that means gamma dot 21 is equal to sigma dot. So now I just need to carry out this integration for this function. So I want you to get comfortable with these little integrations over these discontinuous functions, because this is going to be the fact of life for you for a little while here. All of our functions are like this for a while. So let's try it. The strain 2-1 between 0 and time t is the integral from 0 to t of this function, of the function sigma dot of t prime dt prime. So we just need this function between 0 and t. And this function is being taken, this function is written here, and it's written for epsilon very, very small. So we have our sketch. These kind of problems are best worked out with the sketch nearby. So this is sigma dot as a function of time. This is 0, and this is epsilon. And this level is gamma dot naught. So this interval is vanishingly small. Okay, so we're not going to worry. Actually, I'm not sure. Maybe I did it that way. I guess we can do it formally, right? But we're going to say we know what the function is for time t less than 0, which we don't care about because our integral just goes from 0 to t. So this, we can just use these final two terms. This is the integral from 0 to t of the limit, epsilon going to 0, of its gamma dot naught for t prime. Remember, we're doing sigma dot at t prime as a function of t prime up to epsilon, and then it becomes 0. So I can take this limit to the outside and take the limit later. I have the integral from 0 to t of gamma dot naught. T prime goes between 0 and epsilon, and then it becomes 0. So I'm going from 0 to t. T is some arbitrary time. It's not going to land in between 0 and epsilon because epsilon is approaching 0. So t must be out here. Any time I'm interested in is out here. So that means we can split this integral up as the integral from 0 to epsilon and then epsilon to t. So this is the limit. Epsilon goes to 0 of the integral from 0 to epsilon dt prime of whatever the function is over that range, and then from epsilon to t of whatever the function is over that larger range. From 0 to epsilon, it's gamma dot naught. And when t prime is greater than epsilon, it's 0. So these are discrete functions, and I know you haven't used them that much, but we use them a lot. Integral of 0 is 0, so that one doesn't matter. And so we get the limit as epsilon goes to 0 of the integral of a constant, so we get the constant times the variable evaluated between the limits. And so we get the limit of epsilon going to 0 of gamma dot naught epsilon minus 0. So it looks like the strain is 0, but that's not quite correct because gamma dot naught is not a constant. Gamma dot naught is equal to the strain, which is a constant, divided by epsilon. If I bring back my previous slide here, gamma dot naught epsilon equals the strain gamma naught. So that means gamma dot naught is gamma naught divided by epsilon. So there's an epsilon in the bottom there. So because of this relationship, we have something interesting. We have gamma 2, 1 between 0 and t equals the limit epsilon goes to 0 of gamma dot naught epsilon, which is the limit epsilon goes to 0 of gamma naught over epsilon times epsilon. So the epsilons cancel, and we get that it's gamma naught. So whether you do it formally, like I just did, or more casually by looking at the graph, you get the same result. That for this function, written in this very kind of awkward form, this limit step strain, the strain is given by this amount gamma naught. So this is why this is called the step strain experiment. If after I've taken the limit, it looks like a step-up function. The strain 2, 1 steps up at time t equals 0 to this value gamma naught. This is summarized on the slide. Actually, I did different limits on the slide. The strain between over all times, negative times up to time t, it's equal to the same thing as what I did, but you can also do it this way. Take that limit of the function, and you get the step strain. What does the material function look like? This is an example of real data. This is Ainaga's polystyrene solution data. These are the material functions for the step strain experiment. As you can imagine, if you put a sample between two plates and suddenly move the top one, the stress goes up, the stress relaxes down. If you take that stress, the stress goes up, the stress relaxes down, divided by the constant strain that you imposed, you get the relaxation modulus, and that's what we're seeing here. It turns out that as you change the value of the step, as long as you stay below a strain of 2, or in this case 1.87, stress divided by strain is a constant. This is called the linear regime. Stress divided by strain is independent of the strain magnitude. And so all of the curves are coalescing on the same graph. When you increase the strain higher, in this case up from 3 to 25, stress divided by strain depends on the magnitude of the step. So it depends how far you go. So think of it this way. I've got the sample, and if I take a step and I take that stress divided by strain, I get a number. I get a function as a function of time. If I double the amount, it doubles the stress. If I triple the amount, it triples the stress. This works for a while. That's the linear regime. Double it, it doubles. Triple it, it triples. Quadruple it, it quadruples. But at some point, it doesn't anymore. At some point, the amount of stress that produced is less than double, less than triple. And that's the nonlinear regime. And that's what we're seeing here. These are the nonlinear responses, and this is the linear response. So this is a very common measurement. The linear viscoelastic limit, and we're going to study a constitutive equation that works in the linear viscoelastic limit. This is the material function, g of t. It's a function of the size of the step normally, but in the linear viscoelastic limit, it's only a function of time. This is more sophisticated. We don't need to talk about it that much, but there is a material function defined as the damping function that is defined here that is used to quantify how much this depends on strain. Okay, I'll just leave that. That's advanced information. We can, but I won't take the time to do it, we can predict the step strain response for a Newtonian fluid. Can you guess what it is? If you put a Newtonian fluid between two plates and suddenly did this, would it take a while to relax the stress? We relax instantly. Okay, so for a Newtonian fluid, there would be stress while there's motion, and then it would go away. So in the limit of extremely rapid, you would get the limit of infinite stress during the stepping and then no stress after. So actually for Newtonian fluids, this is a ridiculous experiment because you generate infinite stress for this infinitely short period of time and then nothing. So this is not a reasonable test to do on a Newtonian fluid, and so you'll never see it. But you can calculate it, and you get a delta function. You get that the stress is a delta function during the step and 0 all the rest of the time. Okay, now let's talk about our final material function for shear flow. And this is a biggie. This is an important one that is probably the most measured material function after viscosity. And frankly, it might even be measured more often than viscosity. And that is the material functions in the small amplitude oscillatory shear experiment. So as I said before, all of my material functions have a slide that looks like this. And they define the kinematics, meaning they define what is the velocity field you impose on the sample. And then there are material functions defined that are based on the stress measurements in that flow. So here we have shear flow again. This is the exact same vector every time. It's always the shear flow vector. The only time it's a little different was in creep. And in that case, we didn't have a sigma dot. We had gamma dot 2,1. But here we're going to specify sigma dot. It's going to be this function. So at least this time we're not doing a discrete function, a step up, a step down, or a fast step. We're doing, in fact, a cosine. So this says impose on the sample a shear rate that is cosine. Now actually it's more intuitive to impose on the sample a strain, because when you're not moving, then at least you know the strain is 0. And then you're moving, not moving, moving, not moving. So let's start by looking at this kinematics. Let's find out what the strain is. We know that the strain rate function, sigma dot, is gamma dot naught cosine omega t. What's the strain? This is equal to gamma dot 2,1. Let's start by asking what is the strain in small amplitude oscillatory shear. And we know this also. Whenever I say what is the shear strain, I'm only talking about shear, but I will eventually be talking about elongation. What is the shear strain? We always pull out this equation, the shear strain between 2 points. You have to tell me which 2 points you're interested in, is equal to the integral between those 2 points times the shear rate function of the dummy variable, dt prime. So it's just a mathematical exercise. We can integrate cosines. That's not even hard. Okay, so we put this function in there with the t prime substituted. Integral from 0 to t of gamma dot naught, which is a constant, cosine omega, which is a constant, t prime, which is a variable, dt prime. So this is gamma dot 2,1 of the function t prime. So I substitute t prime in there for t. Now I integrate this. So I integrate this. I have to make this omega, multiply this by omega, which means I take a 1 over omega out. And so I've got gamma dot naught over omega. Integral of cosine of u du is sine of u. Derivative of sine is cosine, so that works. Evaluated from 0 to t, the sine of omega t stays, minus sine of 0, which is 0. So there's our answer. The strain is equal to the sine. This coefficient in the front is the magnitude of the strain. And it's gamma naught again. So for the small amplitude oscillatory test, we impose a strain on the sample that goes back and forth like a sinusoid. And if I go way back to my original slide where I summarized this flow, you'll see that I in fact drew that. Here's the strain, sine of 0 is 0. Here's the strain rate, cosine of 0 is 1. Okay, so here's the strain, it crosses at 0. Here's the strain rate, it crosses at 1. The magnitude is gamma naught of the strain, and magnitude is gamma dot naught of the strain rate. So next time I'll talk about what the stress response is. In the linear regime, the stress response is a wave of the same frequency with a phase shift. That's where the interesting stuff happens, so we'll talk about that next time.